So our work is called Improve MPI Collective for 3D FFT. And first we will introduce how generally the FFT computation problem are solved in parallel. And here's the graph to illustrating the process. And just like many high performance applications, the first thing is to divide the problem into smaller subsets. And one of them is called slab decomposition, which is divide the 3D cube into 2D slides. There are different types of decomposition algorithms, such as the pencil decomposition, which supports a higher degree of scalability. But now we are focusing on a simple method of slab decomposition. And for step one, consider the 3D cube of elements are already divided and allocated to each process. And first, each process are going to do the 2D FFT on the XY plane. And on the 2D XY plane, in our case, is this plane. It's this plane. And for example, the plane of XY, the index starting from 0 to 15 are computed each time. And therefore, it could be done by parallel. And now, since we have solved the problem on the XY plane, and the rest thing is the 1D FFT on the Z plane. And however, the elements are segmented by our dividing algorithm. So therefore, we need to recombine those elements together. So those elements on the same axis are fitting together into the same process. And one of the prevalent solution is to use all-to-all communication, is to chunk each slab data further into smaller cubes, and then each process swap those cubes with each other. And like the process illustrated in step 2 picture and step 3 picture. And finally, the FFT on the last axis could be executed. And there's one problem, is that if we do not change the data layout as it is when we first partition the problem, such as the z-axis, the elements have the biggest stride into the memory. So for the first element on the z-axis and the second element on the z-axis, it's 16. The stride of each element is 16, which is the size of the xy plane, which introduces a very large disadvantage in the cache performance. And our work is to solve that to minimize the overhead. So for the time breakdown of the 3D FFT, I have listed several steps. The first is purely the computation, and it's for the serial FFT for the first phase and the last phase on each single plane or axis. And then it's the data packing and communication time to send data, to swap, to communicate data with each other process. We need to first pack the data, and those elements are in transit into the network. And if necessary, we have mentioned that there's a cache performance issue. If we want to acquire a higher cache performance, we have to rearrange the data from this state, the stride is 16. We have to rearrange data for the last axis to be close to each other, and it's called data rearrangement time if we want to have a higher performance of cache, but it takes time. It's also introduced memory operation. If we do not do that, we will have a longer time on the strided axis of the elements. So this is the problem. And now we are going to introduce the exact data type construction function of MPI data type. The conventional MPI subarray function is used to extract a subarray from an array given. And the arguments of the function is listed as follows: n dimensions and array of sizes. This argument is the global array size we are given to. For example, we are having a 3 times 4 array, 2D array, and the parameter of that is 3 and 4, and number of dimensions will be 2. And the array of subsizes is the array we want to extract from the global array, and in this case, it's 2 times 2. So the array is 2, so the elements in the array is 2 and 2. And the third argument is the array of stars, and in this case is 1 and 1 because the element 5 starts from the first column and first row. And there's an argument called order, which I will introduce later. And for these 4 arguments, we can decide a subarray that we want to extract, and that will pass into the function, and the data type engine will assemble those elements when the communication is taking place. As for order, the original MPI definition only have 2 order definition. It's either MPI data fortune or MPI data C, which is a row major and column major storage. And we are going to extend the definition because for the array that dimension is greater than 2, can be actually other storage orders, although it's not conventional column major or row major. So here we have are going to introduce some limits of the subarray data type. Is only the MPI order C and MPI fortune supported, and that means a structured FT is unavoidable because only 2 types of the storage order is supported. And there's also knowledge that MPI does not require exact match for the data type between sending and receiving function. That is being said that the data type could be like a zipper that are matching close to each other, and the zipper could have different stars, but finally they match to each other. And the MPI sending and receiving is basically like as long as the zipper would fit, and it will have a successful transmission. And based on that, we are going to think about to design in-flight data rearrangement by first extend the subarray data type storage order, and then use the zipper-like storage order pair to perform in-flight data rearrangement. And now we're going to introduce the unconventional data storage that we have mentioned. Is that we can use the conventional MPI order C, which is row major 1, is the first access. The elements of first access are close to each other, like XYZ order, or the column major order is 210, and this corresponds to ZYX ordering. But there could be more combinations. For example, in a 3D occasion, there could be 6 possible storage orders. For example, the 0, 2, and 1. The x-axis, the elements of x-axis has the highest priority, and they are stored close to each other. And then it's the z-axis. So the z-axis are aligned after the x-axis, and then the y order. So the elements in y-axis has the largest stride. And then here we are going to introduce the in-flight rearrangement that could be achieved by unconventional storage order if that could be successfully implemented. So suppose there's a sending type order 1 to 0, and I'm sorry, this is disorder of the slide, and I will go over to this page shortly afterwards. And now we are going to introduce how we create a flexible subarray data type that accepts more flexible data storage order. And the essential idea is that the subarray could be conceived as multiple layers of the H vector, a vector constructor. A vector is is a 1D, one-dimensional array, but after nesting several layers of the vector, it could, for example, by nesting multiple vectors in vectors again, we can achieve the XY plane data type. And by passing the XY plane data type to the vector constructor, we can now construct a 3D array. And based on this idea, we could create a subarray in this way. And here we take this chunk, the second chunk of the first process that is going to send to other process. For the conventional order, the x-axis elements are aligned close to each other, so they have the minimal stride, which is 1. And for the second storage order, which is y, and we have the middle sized stride, which is 8. And for the z, we have the largest stride. Okay, we can now construct a most conventional data type by nesting the H vector and specifying the strides and the block length and the count into the function. Now, let's consider we're not going to make the row major storage order. We want to implement something different. And for the left one is from the left one is the stride of conventional storage order of row major order. That is natural, and we can achieve that. However, if we are going to implement the column major order, and we want the 3 and 4 on the x-axis to have the largest stride, we can simply alter the stride parameter to the largest of them. So now the 4 is no longer in this place. It will be placed into the position where 19 is originally at, and the 19 will be stored at the 4 where the element is originally at. Now we could flexible creating subarray data type, and now we are not only limited to the XYZ or ZYX, the 2 storage and column major. We can have unconventional one as long as we shuffle the nesting order, and we are going to achieve different types of storage order. Okay, since we have developed this scheme, the function, and we're going to explain how the in-flight data rearrangement is performed. Suppose we have already constructed one data type is called 120, and on the receiving side, the data type is 201. And on the sending side, the elements in the y-axis, which is axis 1, are packed first, and then axis 2, and then axis 0. And on the receiving side, the data type engine is first to unpack the axis 2, because we specify that into the first order. And by creating this mapper, the elements in the first axis are unpacked as the last axis, and therefore we have a mapping into each other. And the first axis refers to y, and the second axis refers to z. So YZ rearrangement is performed, and and for example, the 2 maps to 0, and z is mapped to x, and x is mapped to y, because there's 0 and 1 mapping. So therefore, the in-flight rearrangement is achieved. Here's how we create flexible subarray data type: is first to calculate the strides, and then to create a block with shuffle order we desire, and then to append the offset. And with the simple method, we're going to create. We have created this flexible subarray data type. And for the experiment setup, we use the Narvel of Digital Alliances of Canada, and the specifications covered in the paper. And here's the short list. And for the serial FFTs, we are using the FFTW library with a flag of FFTW measure. We're taking this flag because FFTW library provides different flags for creating their calculation plans. This is one experiment from this paper, and we use the value and we show their results. By using FFTW measure time, the setting up time is relatively small, and the computation time is fairly small. We are not using the FFTW patient because the setting up time is too long, and it also has marginal performance improvement compared to FFTW measure. So actually, FFTW measure is the choice of production. From the disparity between the setup time, the FFTW patient only pays off when the execution time is so large. I remember the figure is about 4,000 or 8,000 for 256 3D array in this paper. And however, the in-flight data arrangement type comes with a penalty because it has more complex sending, packing, and receiving packing, which could cause an impact in the communication performance. And we noticed that for our case, we want the second storage order to become the zero storage order. There could be 12 possible combinations, and the time varies a lot. From the longest one, it could cost 5 times as the shortest one. And we're using the shortest one, and it is wise anytime when using our algorithm to first measure the performance of communication, because it's system dependent. It does not happen to be always the second combination to have the best performance of communication. And on this side is increase of conventional non-transposed non-rearrangement MPI subarray. And now we are going to explain where do we gain from the performance, because another important thing is the computation improvement. And for the strided FFT, we have designed an experiment. So the red line is the time consumption of 1D FFT on a single core of the supercomputer, and the stride is always 1. And for the blue one is the strided axis, and the stride is increased as the size of XY plane. So in this experiment, we can see almost twice or nearly twice or third speed gain of the strided FFT. And finally, we have the performance evaluation of subarray. In the whole 3D FFT computation, we have done the strong scaling and the weak scaling. And for strong scaling, we use the 2048 3D complex array, and the cores ranges from 32 and 124. And due to the memory limit, not all of the cores are utilized in the experiment because our computation is out of place, and 256 of memory is not enough to have all the data stored into a single node when we only have 32 cores with one node. And here's our speed up. And for better understanding, we have the time here. It's a strong scaling, and the blue line is using the identical data type without rearrangement in flight. And here the purple line is the computation speed up, which refers to the cache, the strided strided access performance gain, and the blue line and the green line is the total execution time speed up. And for the big scaling, and it's down in this, we have two different sets of big scaling. And the first one, we are starting from 16 cores node to 1024 cores. And this is, and on the left is the time of the time consumption comparison, and on the right, once again, the computation speed up and total speed up. And we have a spike when the core is equal to 1024 which is we are surprised of that, because from the previous test of strided penalty, the speed up should be around 2. And the spike in another setting is more exaggerated, as 9 times speed up and 7 times speed up of purely commutation, when the course is from 1024 and 2048. And for our conclusions, we have developed MPI several data type with arbitrary given storage order, and which we could use it for in-flight data rearrangement, and we have tested the performance, and we have examined specifically the strided access impact on FFT commutation, which is not massively studied in the previous literature, and our method of data movement is have further potential if frequent data movement rearrangement is needed. In such scenarios, it should have better performance. And thanks everyone. Here's my presentation of our work. And next is question time.
Thank you. Any questions in the room or online?
Yes, please.
Yes, I have one question about your results, your last result slide, if you can go there.
Sure. One moment. Share the screen. The last slide. This one or this one?
Yeah, this one, yes. If I understand well, you are computing the weak scaling, but you only test with 32 cores. So how do you 32 cores on the you don't have the sequential time? So how do you calculate the speed up? Because you must have a parallel time times the sequential time to have the speed up. So it's strange to me to not have a sequential time when we are doing strong scaling or weak scaling stuff.
For the sequential one, do you mean the sequential one is all the data computed in a single core?
Yeah, I guess the question is, what is your reference? What is the baseline here?
The baseline, yes.
Yeah, so for the 32 cores is we utilized a single node with 32 cores. So the 32 refers to one node and 64 refers to nodes. We are doubling the node count each time while the cores of each node is unchanged. And this is our methodology.
What are you comparing against?
Comparing, so are you referring to the blue line? Is the using original MPI storage order, and which incurs the strided FFT, and the blue line is the total execution time of using that method, which is brought by Dr. Dowson in 2019.
Okay, does that answer your question?
Yeah.
Okay. Any other questions? Online, someone? If not, I have a question. We have 5 more minutes. On this slide, so do you have an intuition on why the computation speed up increases so much in the end? Is that because?
Yes, please.
Yeah, is that because of better cache use? Because this is strong scaling, right?
This is weak scaling, and no matter and strong scaling, we both have observed a strange spike in commutation speed up, and from the reviewers, some of suggesting we look into the cache, but at that moment, we do not have enough time to do further investigations. So it's really a good advice if we could down the cache hits statistics to explain this phenomena.
Okay. Thank you. You have.
So where is the arrangement of the data being done? So it's you prepare the data before sending the message just directly in the node, or I didn't get when you do the rearrangement.
Okay, let's go back to the rearrangement. Is it here for the data arrangement? How the data arrangement is done by the different sending and receiving pairs are performed? Is here that you are interested?
Yes.
Yeah. So for this, for here, we want the sending order that's stored with 1 to 0, which means the elements of the second axis or the y-axis are packed close to each other, which is what we conventionally think is x-axis, and the data types packing engine will pack the y-axis data as x-axis data. And here, and the unpacking process is to unpack what we originally think the z-axis into the x-axis. So here's a mapping of the sending and receiving pairs, and here the y-axis becoming the z-axis, and the z-axis are becoming the first axis, which is x. And here the xyz to z yzx transpose is performed.
I think the answer to your question is that the MPI data type engine does the transpose for you. So the sender describes the data in one way and the receiver describes it in the transposed way, and MPI will take care of moving the x-axis to the y-axis, or whatever combination you choose. Right?
Yeah, so it's in the receiving part that
it will most likely
it reads differently.
Yes.
Yeah. Okay. Thank you.